It's called Adaptive Filter for Radio Frequency Interference Mitigation, implemented in Roach 2. As I was introduced, my name is Franco Curotto. I'm from University of Chile, and specifically inside the university, I work in the millimeter wave laboratory, where we have been working more than 8 years in Casper hardware, specifically Roach and Roach 2. And what we do is mostly academic research around digital systems. So here's a brief bullet point of all the work that we have done. We have done calibration for side-by-side separating receivers, calibration of orthogonal transducer. We have also played with beamformer for telecommunication system. And my work specifically, that's adaptive filter for FI mitigation. These are links that you can then check when you have the slides, that's the group. And we mostly try to convince telescopes to use digital systems. Okay, so the specific problem that I'm trying to solve is the radio frequency interference. That many may know that this is a very huge problem in radio astronomy. So what is happening basically that all our telecommunication systems, radio towers, radar, etc., are corrupting the measurements of the telescopes. And my personal favorite is the microwave ovens that have been shown in the news that even our own system of the observatories can affect our own measurements. So, as I said, this is a very hot topic. In your left, you see a poster of a workshop, an RFI 2016 workshop around only talking about RFI mitigation techniques. And on your right, you can see a special issue of the journal Astronomical Instrumentation dedicated to mitigation techniques in radio astronomy. So unfortunately, I wasn't able to go to this place and I wasn't able to publish here just because I wasn't aware of. So this is kind of my revenge where I can finally present my work. Okay, so now to the specific implementation of my solution, or what I'm trying to propose as a solution. It's called an interference mitigation adaptive filter. So what is this? It's basically a system where you have to put a reference antenna. So you have your telescope that is measuring an astronomical signal, and then you have a separate antenna that is called reference antenna that is measuring the interference that's also corrupting your astronomical data. And what you're trying to do, in very broadly speaking, you're trying to cancel both measurements of the interference doing a subtraction. And to make this subtraction as perfect as possible, you have here a system that's called an adaptive filter that's trying to make both measurements as equal as possible to make the cancellation. Okay, so the idea of this kind of system is that you hopefully don't lose any of the data because you subtract all the interference and you keep the astronomical signal. So you don't have to blank the data or lose data in the process. Okay, so now let's talk a little bit about the math of how this works. So the simplest case is to assume that your RFI signal is a monochromatic signal, so like a pure tone. So you can assume that you can represent this interference in the telescope as a magnitude I and a phase theta I. And in your reference, you take a second measurement that I call R theta R. So both of these signals are not the same, so they have a difference in magnitude and phase, and that's because they take different paths through the sky, through the atmosphere, and they are measured by different systems, right? But they are certainly correlated in some way. So then you can go to a typical system that's digitalization, frequency, go to the frequency domain through fast Fourier transform, and then you have your reference signal, and you want to transform it into your interference signal in the telescope in order to make this perfect cancellation. So in this simple case, you can very easily see that the way to do that is that you have to multiply your reference signal with this parameter that I call the filter parameter that is represented by a ratio of the magnitude and a phase difference. So if you multiply these two values, in the complex domain, almost by cancellation, you get your original interference signal, and then you can do your perfect cancellation. So that's the justification. But the problem here that you're trying to solve is exactly how to compute these parameters in as accurate as possible. Okay, so this is the math that tries to explain how this is done, right? So this is a simplification of the system. So basically, you have to do two steps. You have to compute a correlation, like we usually do in correlators. But in this case, you have a feedback system. So you have your filter. And this is feedback to the beginning of the system, and you may compute the correlation between your reference signal of your reference antenna and your filter output. And when you do that, thanks to the properties of correlation, as we saw in day one, you got this operation of correlations between the filter output that in the first iteration you can think is only the astronomical signal and your interference signal. Then through the properties of correlation, you get the correlation between the astronomical signal and the reference signal. And since this is interference, you can assume that they are not correlated, and this operation is zero. And you only get the correlation between your both measurements of your interference signal. So this gives you, in the frequency domain, as you may know, the multiplication of the amplitudes and the phase difference. So this is good, because this term, the phase term, is what we're looking for. Now we only have to get the amplitude ratio instead of the amplitude multiplication. So this is done with a second step, where you multiply all the correlation results by a gain parameter. This gain parameter is called epsilon, and it's a user-defined parameter. And if you have perfect knowledge of the system, you can set this parameter to the 1 over r squared, if you know this magnitude of your interference. And the output of this multiplication will be exactly the interference you're looking for, and you'll get perfect cancellation at the subtraction. Okay, this is good if you know you have perfect information. But if you don't know, you can estimate the amplitude of your interference, and you have to only stay in this interval in order to the filter to work properly. Because even though if your estimation is not perfect, you get an output that is estimated as the interference you're looking for, and over many iterations, because this is a feedback loop, you get that your filter converts to the cancellation of the interference. And the only thing you have to avoid is that your epsilon value is not too little or too high, in order to avoid the filter divergence. So this is the map of the system. Hopefully you understand something. And now we're going to the implementation. So as I said at the beginning, the implementation is done in Roach 2 hardware with the typical ADCs, 5G for digitalization. So as you can see, this is done in Roach 2. It's very sad for me to hear that Roach 2 is getting deprecated. But okay, that's the way to go. If anyone here is still using Roach 2, we maybe can do a group and help each other, or maybe party and do our conference. I don't know. So, well, as you may know from yesterday, all this implementation is done in Simulink. So I basically omitted all the spectrometer stuff, because that's like very standard, and I only put the filter stuff that is like the new thing. And basically you got all the multiplication, the others, the accumulation, given on the filter. You can see that it's very simple. And this is added to the spectrometers in order to create the full system. And in the table below, you can see the information about the filter, the complete filter. It has a bandwidth of 1 gigahertz, a frequency 4096 frequency channels. That gives you a frequency resolution of 244 kilohertz and a dynamic range of 86 dBs. So perfect. That's implementation. We understand the math. And now let's see the results, right? So the first set of results that I made is a laboratory test. So you can see that it's a very simple diagram where my astronomical signal is simulated with a noise source and my interference is simulated with an arbitrary wave generator. I combine them and then I fed it to the Roche board. Let's see how are the results. You can see on your left that that's the primary signal that is entered to the, this is emulating what you see in your telescope, right? So you have here the flat signal represents your astronomical signal, and the spikes represent your interference. So you want to eliminate the spikes, right? And in your right, you can see the results. So the blue is the original astronomical signal, and the red is the filter output. And you can see that visually they are very alike, right? Even they are so similar that I had to put a 10 dB offset so you can see the difference between the two plots. This is in frequency domain, obviously. So in numbers, the attenuation that I achieved is at least 35 dBs, and the attenuation speed to 1% of the interference power is 2 microseconds. Okay, so this looks very well. I present this to my supervisor, and he said, oh, this is perfect, but you know what it would be even better? To prove it in a telescope. So that's hard to do to get my title of master engineer, so I had to do it. And here's how I prove it. So you can see here that I use, this is the system that I use to test it in a real environment, right? So I use something that's called a small radio telescope. There is a telescope designed in MIT, in the HICAT Observatory. And for the reference antenna, you can see that you can use any type of antenna. So I use a simple dipole commercial antenna in the frequency that I was testing, that was 1.4 gigahertz. So this was going to measure the interference, right? And then this is the analog system that we don't care much about here, right? So I'll just keep it through. And let's see the results. So what I was measuring here is 1.2 gigahertz, and I was pointing to the sun. And here you can see a spectral plot of my result. So now you can see that in this case, the filter is attenuating the interference. Oh, so the interference is given again for are these spikes here in the plot, right? So I have no idea where the interference was coming from. I was in the middle of the city. I had multipath refraction from all well, the buildings, etc. And also I was measuring in a reserve band for radio astronomy. So this shouldn't happen, but you can see that I can see it anyway. So you can see the results. So here's a close-up of the system, and you can see how the attenuation of the filter, but it's not complete cancellation, unfortunately, in this case. And here is another way to see the cancellation. Here, the 0 degree offset here is pointing to the sun, and you can I make like a left-right scan, right? So you can see at the middle you should see the maximum power, and on the both sides you should see a symmetrical like plot. But at one side I had interference, so I have like this spike. My filter helped with this plot, with this measurement, but you can see it's not perfect. So you can see it works, but it's not work as perfect as you would like to. So the question is why this case, in some cases, doesn't work. So the answer that we arrived is that in the real scenario you get, especially you are in the city or in a bad place for astronomy, you got multipath propagation on your interference signal. So you're getting not only interference directly from the light of view of your RFI source, but you get reflections, right? So you get multiple interference entering into both of your receivers. And why is this a problem? Because mathematically, the filter worsens its performance if it's affected by multiple sources that are not correlated. So you can prove this mathematically, but I will do it just with a simple diagram. You have one type of interference and another type of interference, and they both combine and enter to the filter. You get that you only attenuate the highest power interference, and only to the point where both interference get the same power. So this is like a limitation that you have. So you have to live with that, basically. And well, that's that's all that I wanted to show. So in conclusion, the implementation of the filter works very well, where you can achieve at least 35 dBs of attenuation, but in the cases where you have high power, narrow band, and well-defined RFI, right? So when you have like a clear view of your RFI, you know where it's coming, you don't have multipath, that's like the good case. And the filter performance worsen when you have RFI affected by multipath propagation or multipath RFI in the same frequency band, etc. And as a future work, unfortunately, the only site I had to test this was, as I said, in the middle of the city. That was in the University of Chile. So I would like to test in a site less polluted with RFI to see if they have better results. And another way that I'm thinking I can solve this is to increase the frequency resolution of my spectrometer, because that will give me, like, even if I have two RFIs very nearby, if I can resolve it with very good resolution, I should avoid a little bit this worsening the performance. So I was hoping to build a mega-channel spectrometer, but I wasn't successful. But that's why I have been asking to some people if someone has implemented this in Roach 2. And I would like to hear if anyone knows, or I will be still asking. So that's all. Thank you.
So I have a question about your adaptive filter.
Yes.
Is it a real-time filter, or are you updating the parameters in real time?
Oh, okay.
If you are not, how long does it take for parameters to get stabilized? And do you optimize the parameters?
Yeah, that's a good question. I think that I didn't explain it well. The idea of this is to be like automatically, right? So you have your antenna, you have your telescope, and this is computing this correlation like every cycle, right? So it's done automatically, basically. So you can point to another place, you can get different interference, and it should cancel this new interference. Yeah. Yes?
If you have a large array, how often do you need to place it?
Okay, so yeah, that's another thing that I didn't explain well. This is focused in single dish antenna. You have an array, it gets a little bit complicated. I actually have read similar implementations where you use one of the antennas of the array, you use it as a reference antenna. But of course, no anyone would like that, because you're losing an antenna. But it's an interesting question. I can give you a number. I think you can get away with one, but if you have like multiple R5, maybe you will need more.
One last question.
Is it possible to put multiple reference antennas around the dish to get an average interference signal? It's not in the focus of the parallel, but on the edges, capturing the noise.
Maybe yes. You ask for like measuring different interference that one antenna can capture. Okay.
Yeah. So you have several, maybe 4 RF antennas at the edge of the parallel.
Yeah, probably, but you will have to implement like multiple filtering cascades probably. So it's more complicated, but it should work.
Okay.
Okay.